Hello, so when I signed up for this conference, I had to go into the web page and I had to put in my name into this web form, which I'm sure we have all seen. We all signed up for this conference. So. But one thing I didn't expect to happen there was that the web page would keep deleting a character from my name, which was of course a bit annoying since it made it a bit hard for me to sign up. But anyway, it's not a big deal. It's just that I have a Danish character and therefore it removed that Danish character, which I suppose the backend didn't support, and therefore the frontend tried to prevent it from putting that in there. This is kind of a good example of that we need to be careful when we're using strings, since string is really the main way that a user can put things into the program. And if we're not careful as programmers while getting those strings, bad things can happen. So for instance, we can look at this XKCD where you have an unsanitized string that is being put into the database, and they lose the entire user's database in the end. This is of course not cool. So we need methods for analyzing string constraints, or not analyze string constraints, but at least analyzing programs with strings, which result in string constraints. This is what we're going to look at in this work. And now you might have been surprised because I didn't actually introduce myself. I am Danny B. Poulsen. My co-authors of this work is Mitya Kuczynski, it's Dirk Novodka, it's Florine Vanea, and it's Joel Day. Okay, so we're going to look at string constraints, and in particular we're going to look at something called word equations. Before we start talking about how we solve word equations, it might be adequate to actually look at what is a word equation. So a word equation is something like this structure where you have two sides of an equality, and on both sides there can be terminal letters, which are the lowercase letters in this case, and there can be uppercase letters, which are variables in these examples. So how do you solve a word equation? Well, you try to find a string of terminals that you can assign to the variables, such that when you replace the variables, then the two sides will unify and they will be equal to each other by just position-wise. Right, so for one word equation this is fairly straightforward, and not fairly straightforward, but it's fairly easy to see that problem. Now, of course, you can imagine you have a long list of word equations that you want to solve, and then of course, in order to solve all of them, you need to refine a replacement for the variables which matches all word equations. Fairly straightforward. So this is a fairly easy thing to explain, and it might not seem very hard, but actually this is a very hard problem, since the problem is, in regards to solving these, is that the variables can be replaced by arbitrary length strings. So it's not like you have a finite length that the variables can be, and as you don't have that, you don't know how long you have to search. So it could actually be a very difficult problem. Luckily, it is solvable, it is decidable, and the reason it is decidable is because Plantovsky, or one of the reasons is Plantovsky found a bound that for how long substitutions for variables you sort of have to search in order to find a minimal solution, a smaller solution for this for the equation. So that means that if you go beyond that length and if you go to that length and you haven't found a solution, then there cannot be a solution. Very simple. The method we use for solving word equation in our work here is that we transform the word equations into the word equation we want to solve, we transform that into another word equation. And of course the hope is that other word equation will be easier to solve than the original one. Okay, so in order to do this, in order to transform them, we need to look at different scenarios sort of in the word equation. So the first one is, if the prefix of the two word equations, or not the two word equation, if the prefix of the two words that are part of the word equation is the same, then we can chop off that prefix, since it doesn't matter for the final solution what that is. The prefix will always line up. Okay. Second one is, if we have the left-hand side starting with a terminal and the right-hand side starting with a variable, then there are sort of two cases. Either the variable is the empty word in the solution, so in that case we can chop that, we can just remove that and do that consistently throughout the entire word equation. Or the alternative is that the variable actually starts with the terminal, in which case we can transform this word equation into this next one you see by replacing the variable by the terminal followed by the variable. And now if we have a solution to this transformed one, we'll have a solution to the original one by just doing the map, this replacement in the reverse somehow. The final case we need to look at is if the left-hand side starts with one variable and the right-hand side starts with another variable. In this case, one of the variables could be the empty word in the final solution, or let's say the left-hand side is a prefix of the right-hand side. And if that's the case, well, then we can say the right-hand side variable is just replaced by the left-hand side variable followed by the right-hand side variable in the replace one. Great, so now we have a way of transforming one word equation, but we of course need to do this for the entire word equation system. So if we have many of the word equations, we need to do it for all of them. Now the strategy for this is actually quite similar. What we do is we just pick out one word equation, find out what structure, what rule we have to apply for that one, and then we just apply that transformation throughout all of the word equations for that point. Okay, now if we do this, this gives us kind of an algorithm for solving word equation system. So what we will do is we will start out with the first word equation, then we'll apply one of these transformation rules and get a new word equation out of that. That new word equation will be put into a set, not just one word equation, we'll generate all the possible word equations we can from that by applying different rules. Okay, so this will give us new word equations, which we will then have to search for. Whenever we pick up a word equation, a new word equation, we will look at it and say, is this trivially satisfiable? If it is, then awesome, we have a solution to the original word equation, and we can find out what that solution is by just backpropagating the trivial solution we found for the last word equation back upwards to the original one. If it turns out that it's trivially not satisfiable, then we just stop searching that word equation at that point. Nothing fancy there. On the other hand, if it's neither trivially satisfiable, not trivially unsatisfiable, then we apply the rules for that one, for that new word equation, and we get a new word equation we have to search. So does this terminate? Not necessarily, actually. Of course, what we can do is we can keep track of what word equation have we already looked at, and if we come back to one of those we already looked at, then we just don't look at it anymore because we know we have searched it. But there's no guarantee. There are examples of word equations that will expand a lot while searching for a solution. Luckily, Plantovsky's bound sort of saves us in this case, since we can just search to sort of until we have exceeded Plantovsky's bound and the minimal within the bound where we would have found a solution somehow. So you're going to imagine you have this big tree, and then there is some area, some point where we know that if we search more from here on, there will not be a solution no matter what we do. In the algorithm we just saw, I said we had to figure out whether an equation was trivially satisfiable or whether it was trivially unsatisfiable. So in order to figure out whether it's trivially satisfiable, we can do the simple thing and just go to the case where the two sides are the empty words, in which case we know it's satisfiable. It's trivial, very, very simple. The other cases, the trivially unsatisfiable cases, those are the ones where we have some terminals that are not lining up in this prefix or in the postfix. Right. Now, going to that extreme case where we have them both where we have trivial, it's not necessarily a good idea. So instead, we are going to do the following. We're going to, at given specific times, we're going to allow our algorithm to call out to an external solver, which can handle also word equations themselves. So in our case, we use Z3 and CVC4. So these are two big SMT solvers. And we ask them to try to solve the word equations for us. If they manage, then we can use their solution and we can backpropagate that one to the original solution. So you could ask, why not just use the SMT solver to begin with? And well, the reason is actually that our technique does help the SMT solvers. It does allow this modification sort of guides the SMT solvers. It's not that they guide the SMT solvers, but it transforms sometimes the equations into something that is easier for the SMT solver to handle. And our results show that we can increase the number of word equations that the SMT solvers can solve. Great, so now we have a solution for another solution, but we have an algorithm for finding solutions to word equations. But in practice, word equations are really just the simplest kind of constraints we derive from a program execution, or from analyzing a program. In reality, there are usually extra things on top of it. There can be regular constraints, which are these variables has to be part of this regular expression or whatever like that. Or it can be expressions over linear constraints over the length of variables. These are the ones we're looking at. We're just looking in our paper, we're just looking at linear constraints over the length of variables as the second kind of constraints we add. Something that is a bit interesting is that even though word equations are solvable and is a decidable problem whether there exists a solution, we're not quite sure about word equations and with linear length constraints on top of it. And the reason we're not sure about that is that you can imagine this. The reason word equations, finding a solution to word equations is decidable is because we can just go to the Landowski's bound, and when we exceed Landowski's bound, then we know that there cannot be a solution anymore. Imagine in the transformation system. But it could be that there is a solution to the word equation within Landowski's bound, but that solution does not satisfy the linear constraints on the length. And therefore, you cannot just stop after Landowski's bound, but actually it has to search onwards, because there could be a solution somewhere in the future, somewhere along this huge transformation system. There could actually be a case where you have a solution to the word equation and its solution to the linear constraint, but if you stop before that, you will not find it. Anyhow, the way we handle these linear constraints in our work is that we, during the transformation, actually transform the linear constraints in the same way that we transform the word equations. So whenever we replace a variable, we also do a modification to the linear constraint. I'm not going to talk about how we do this right now, but you can read it in the paper, which is a good paper, by the way. It's awesome.